Hi teachers. Today let me and our group members to introduce the application of linear systems in science and engineering. Hi, I'm the first member. My name is Shao Tianyi. You can see it here. And first part, I want to say the introductions about the linear systems. I think linear system plays a very important role in variable fields, enable us to model and solve complex problems in different areas. So through the study of the linear system, we gain a deeper understanding of relationships between the variables, and we can make predictions, optimize process, and make informed decisions. So a linear system consists of linear equations that describe the relationships between the different variables. Each equation represents a linear constraint on the variables, and the solution to the system represents the value of the variables that satisfy all the constraints simultaneously. So these systems can be represented using the matrix notations, where the coefficients of the variables and the constant are organized by vectors and matrix. In matrix, one of the key applications of the linear system, I think it is of course in engineering, where they are used to model and analyze natural language control system, input and output, something like that. So by formulating the equations of these systems as a linear system, engineers can predict the output, can predict the behavior of the system, design optimal control strategies, and troubleshoot any issues that may occur. So overall, I think the application of linear system is vast and diverse in different areas, spanning across multiple disciplines. So by understanding and analyzing the principles of the linear systems, the college students like us can gain some valuable insights to it, make accurate predictions, and solve some complex problems by the tool of the linear system. So let's talk about that. Let's see some detailed examples. So here is the application of the linear systems. First one is economic applications. We'll begin with an economic applications or a simple model. You know that the linear system are used to represent a wide range of the economic relationships, such as price and quantity, income and the consumption, and the supply and demand. So these relationships help economists to understand how changes in one variable might affect another. So typically used, here's a simple use of the linear equation in economics is to determine the break-even points, where total cost equal total revenue, resulting in neither profit nor loss. If the cost function, let's assume that it's represented by the Cx equals to 50x plus 200. And the revenue function is represented by Rx equals to 70x. So we can find the break-even point by setting that the Cx equals to Rx. So it is not difficult. So 50x plus 200 equals to 70x. So we multiply the two sides by the 50x to 20x equals to the 200 and x equals to 10. So by the total of the linear systems, we can find that when we sell 10 units of these products, 10 units of these products is the breakpoint. Sorry, I touched it wrong. So then is the applications, and it is a second example about the applications in chemical reactions and the balancing equations. So for example, we know chemical reactions is that the boron sulfate reacts violently with water to produce boric acid and hydrogen sulfide gas to give the smell of rotten eggs. The unbalanced equation is that B2S3 plus H2O equals to H3BO3 plus H2S. And we assume that there are different X for this. chemical things. So X1 B2S3 plus X2H2O equals to X3H3 BO3 plus X4 H2S. So by finding the whole numbers for X, where the total numbers of atoms of each type that must be same on the each side. So we need to construct an argument matrix and to do the row reduce. So we must find the boron atoms must be the same number and the hydrogen and the oxygen so that we can get the 2x1 minus x3 equals to 0 for the B2S3 and the H3BO3. And the second one is for the, I think it's for the S, yeah. And the third one is for the hydrogen. And the last one is for the oxygen. And we take all these numbers into argument matrix, so we can got things like this. Yeah, and we do the row reduce to the actual form and find the actual form, and at last we can get the matrix like this, and we can got the equations more simple. So we got the relationships between the different x, and we can find one the solutions for this numbers is that the x1 equals to 1, x2 equals to 6, x3 equals to 2, and x4 equals to 3. So my groupmates will introduce more examples to you.
Hello, my name is Gao Haoyang. Now I will introduce linear algebra in electrical circuits application. The tool of linear algebra can be used to study the application of resistor networks. An example of an electrical circuit is below. Okay, as you can see, the diagram below consists of 4 circuits, and the current in the 4 circuits is denoted by I1, I2, I3, and I4. And we can use Kirchhoff's law to write an equation for each circuit and so for each current. So the Kirchhoff's law is that every divides this voltage, and in the circuit, and the sum up the total voltage should be 0. So we can start from the top left circuits here. And I2 here, it goes to the right, and I1 here goes to the left. So the current flow through this resistor should be I2 minus I1. And the voltage should be the resistors multiplied by the current. So it should be 2I2 minus 2I1. And it's the same to the 4O here and the 2O here. So the total equation should be 2I2 minus 2I1, which is the voltage of here, and 4I2 minus 4I1, which is the voltage of here, and plus 2I2, which is the top 2O. And all this sum up, it should equals to the source voltage 18 volts. And the other 3 circuits are also the same, so we can get the other 3 equations, which is 4I3 minus 4I2, 6I3 minus 6I2 plus I3 and plus 3I3. So here should be 3I3 equal to minus 27. And 2I4 plus 3I4 plus 6I4 minus 6I3 plus I4 minus I1 is equal to 0. And 5I1 plus I1 minus I4 plus 2I2 minus 2I1 is equal to minus 23. And now from this 4 equation, we can get argumented matrix, which is downloaded here. And the first row comes to the first equation, and here which is the I1, and the second number is I2, the third number is I3, and the 0 is I4 because the first equation didn't have I4. So, and we need to simplify this matrix, and we can use R3 minus 1 over 2 R1 and minus R2, and then we can turn this one into 0, and then we can use R4 minus 4 R1 minus plus 15 over 2 R2 and minus R3, which can turn this to 0. And after simplifying, we can get the final answer is I1 is equal to minus 3am. and I2 equals to 1 over 4n, I3 equals to minus 5 over 2n, and I4 equals to the 3 over 2n. And another application is in the population dynamics in biology. Population dynamics is a field of biology that studies the size and age communication of populations as dynamic systems. It examines how population change over time, and the factors that influence these changes include birth rates, death rates, immigration, and emigration. Linear systems play a crucial role in modeling and analyzing these dynamics. And there is a model, it's called the linear matrix model. This model is a discrete age-struct model of population growth. It uses a matrix to represent the transition of individuals between age classes from one time step to the next. First one is age classes. It divided the population into discrete age classes. For example, a population might be divided into age groups of 0 to 1 year, 1 to 2 year, and so on. The other one is the second one is linear matrix, which we use L. The square matrix, which each element Lij represents the transition rates from age class J to the age class I. The first row contains the fertility rate, and the sub-diagonal contains the survival rate. And the third one is population vector N, a column vector representing the number of individuals in each age class at a given time. And the fourth is the model equation. The population at the next step, nt plus 1, is obtained by multiplying the linear matrix by the current population vector nt plus 1 equals lnt.
Okay, now let's start the third part. The linear matrix model. You can consider a population divided into 3 age classes: 0 to 1 years, 1 to 2 years, and 2 to 3 years. The Leslie matrix L and the population vector N might look like this one and this one. And the 0, 1.2, 0.8 are the fertility rates for age classes 1, 2, and 3. 0.50, 0.7 are the survival rates for transitioning from one age class to the next. The population at the next time step, nt plus 1, is calculated as. And the case study, fish population management. Suppose a fishery management wants to model the population of a fish species divided into 3 age classes: juveniles, subadults, and adults. The Leslie matrix for this population might be like this one. And you can give in an initial population vector n0, 150, and 30. The population vector at the next time stop n1 is n1 equals L plus L minus n0. And the manager can use this model to project future population sizes, evaluate the impact of fishing policies, and ensure sustainable fishery practices. And also it also have some benefits and limitations for the linear system. The first one about the benefits. The first is easy to understand. Linear systems are relatively simple compared to nonlinear systems, making them easier to study and analyze. And the second one is useful in many fields. They are widely used in engineering, physics, economics, and other scientific areas to describe and predict system behaviors. And the third one is good for analyze and design. Linear models help engineers understand how a system responds to different inputs and support the design of control system. And also it has some limitations. The first one is not always realistic. Many real-world systems are not linear, so linear models can only provide an approximation. And the second one, it has limited accuracy. The model may become less accurate when operating conditions change significantly. The third one, it cannot describe complex behaviors because some system characteristics and interactions cannot be fully represented by linear equations. So let's have the conclusion. In conclusion, linear systems are important in science and engineering because they provide a simple way to study and understand complex problems. Although they do not perfectly represent every real-world situation, they are often accurate enough for analysis and practical applications. Their simplicity and effectiveness make them a fundamental part of model engineering and scientific research. And thank you for your watching. That's all for our part.